Hello, Babita. Are you there?
Yes, sir. Yes, sir. We'll start.
Okay, no, yeah, I just want to make sure you can hear me. Okay, so yes.
So 2 minutes left. We'll
That's
start.
That's fine.
Welcome back, everyone. So the next talk of the day will be by eminent Professor Ajit Mahapatra from University of Wisconsin-Madison, US. We heartily welcome you, sir, to the webinar. Professor Ajit Mahapatra is an experimental particle physicist and is currently working as a researcher in the physics department at the University of Wisconsin-Madison, US. He received his PhD in physics from Utkal University in 2000 based on his research work conducted with the Belli particle detector at the High Energy Physics Research Lab in Japan. He joined the physics department as an associate researcher in 2005 and has been involved in one of the Large Hadron Collider experiments called Compact Muon Solenoid. His primary focus has been the physics computing aspect of the experiment, and he is responsible for the operation and management of a large T2 computing center dedicated to the CMS experiment. As a research associate at UW-Madison from 2001 to 2005, he was involved in the B. Mason factory experiment using the Barber detector at Stanford Linear Accelerator Center, US. Prior to that, as a postdoc at University of Cincinnati during 1999 to 2001, he participated in the Hera-B experiment at Daisy, Germany. He has been a part of many fascinating and challenging high-energy physics experiments for the last 28 years. With this short biography, I welcome you, sir, to deliver the talk entitled as Grid Computing for the Large Hadron Collider. Sir, please.
Thank you, Saparja, for your kind introduction. And I'm actually glad to be here. And thanks to my dear friend, Professor Oja, for her invitation to participate in this nice webinar. And I'm actually being honored to share my experiences so far with the LHC regarding the grid computing that I have been working on for the last 17 years with the LHC experiment, the CMS, particularly the CMS detector at CERN. Okay, I'd like to first share my screen, my slides. Okay, can you see?
Yes, sir.
Yes.
Okay. Okay, so let's.
Ajit sir, please make a video on.
Oh, just a minute. Okay, just a minute. Okay, is there?
Yes, yes.
Okay.
Yeah.
Okay, so okay, so I will pretty much. Yeah, this is essentially my first slide. Okay, this is pretty much the outline of my talk. I will kind of briefly talk about particle physics because I'm just to share the knowledge with the students. And Large Hadron Collider that is being carried, that essentially is being right now in operation at CERN in Geneva, Switzerland. I'm particularly involved in the CMS experiment, which is compact muon solenoid detector there. And then followed that, I would talk about the grid and why actually the grid was so important for, for the LHC and how actually it has helped with the, analyzing the vast amounts of data that has been collected at the CMS detector particularly, and the other, including the other detectors, that other three detectors that actually part of the LHC experiments. Then I'll focus on the LHC computing model and how it was implemented, which actually has been the backbone of the whole computing at the LHC. And then followed that, I will talk about a Tier 2 center, which has been in operation at UW-Madison, dedicated to the CMS experiment for last 17 years. Okay, then I'll present my concluding thoughts. So particle physics, I'm just kind of going to go briefly on this. Particle physics is, there are two components, two parts to it, theoretical particle physics and the experimental side. And theoretical particle physics is giving us all the insights into the branching fractions, cross sections, interactions, and all kinds of strong, all these forces that actually helps interact the particles, the fundamental particles, the electrons, muons, and the hadrons, and all the other details that actually are involved in that. And that the theoretical part also, they do make predictions and provide us, some kind of a thought, what kind of particles are there or could be there, and how those could be kind of found out, or could be seen, or could be detected, actually. And then so complements to that is the experimental side, which follows through this kind of the theoretical part, and then tries to kind of detect if such particles exist, and to prove that what are the properties are and how they match the theoretical expectations or theoretical predictions, all the details. So I will pretty much talk about so the experimental particle physics side today. And in order to perform a particle physics experiment, the tools that we need are particle accelerators, particle detectors, and we need a ton of computer. And you can see here on the plot that the size of, how things, so the atoms, the electrons, protons, and the quarks, the dimensions. And the LHC, of course, is essentially going to, in the LHC, we do use proton and proton collisions, as I will talk later, which pretty much you can kind of at the core of it are the quarks and the gluons, which do most of the interactions. And in the experimental particle physics side, the scientific process can be broken down into four segments. First, the science device, which produces lots of data depending on how the collisions and depending on what the interactions of particles are. And then those data are kind of collected by the data acquisition system along with, using a trigger electronics, and then which is then fed into the software and computing domain. And then from that, the science comes, the results comes out, and then they go into the journal publications. So that means in order to summarize, petabytes of data gets reduced to a social media post like, what do you say? Okay, finally Higgs was found. I mean, in order to find a Higgs signal, we had to really go through petabytes of data that was collected and analyzed. So this is kind of a global picture of a scientific process. But at the core of it is the data. It's all about the data. Means you have to dig through mounds of data to find something that you are looking for, so that you can verify that it is there or if it is not there. So just to give you a glimpse of the size of the data at the LHC, we're talking about a petabyte of data that is being produced, petabytes of data produced every year. And this plot pretty much shows like a petabyte of data kind of from 1 to 50 petabytes. So you can imagine, you can go through this list. It's a really humongous amount of data that needs to be analyzed in order to find something meaningful, like at the end. So it's a lot of work to dig through, collect the data, then process it at the end, then analyze it, and then find something. So coming back to how this is done at the Large Hadron Collider experiments. So here is a picture of the Large Hadron Collider, which actually is a proton-proton collider, high luminosity proton-proton collider at CERN, Geneva, in Switzerland. This is essentially, so in the picture you can see that that's the large ring. That is where the detectors. That is the 4 detectors are sitting in that ring, along that ring, and that ring is where the proton and proton are being collided. Those are traveling in opposite direction. So this pretty much shows the picture of the ring, and that is sitting in Geneva, but part of it is actually in France, and the other part is it's essentially in the border between France and Switzerland. Okay, and the small ring that you see there, that's where it essentially, the proton initially gets subjected to that ring, and it acquires more energy, and then it's finally gets into the bigger ring to attain the final energy that is required to make the collision meaningful. Okay, the Large Hadron Collider, why it is called the Large Hadron? Because the large part belongs to the largest and most powerful accelerator in terms of the ring size. It's a 27 kilometer ring where the beams actually they circulate and then collide. So that is large. That is why it's called large. And pretty much the whole ring consists of superconducting electromagnets. Just to give you a number, there are actually 1200 dipole magnets along that ring which bend the beams, and 392 quadrupole magnets which focus the beams. And that's how those are actually required to keep those proton beams on their track, on the path, and so that they can collide. And in order to keep those beams in those what do you call on their track, on their path, the electromagnets are actually made up of superconducting coils, and those are actually chilled to minus 271 degree using liquid helium. So with that, the proton beams pretty much travel in opposite directions in these separate beam pipes, and in order to they actually those beam pipes are kept at ultra high vacuum, and then the protons they do collide at 4 interaction points along the ring. So here is some statistics, some parameters I would say about the beams, the proton beams. So you can see here in the beam in the proton the beam pipes, there are the proton beams actually are created in bunches. They circulate in those pipes, and then out of the bunches, they kind of they collide head on. So essentially protons from each branch collide with each other. But then but you can see at the end, it's the which quarks and gluons, they do in fact, collide. Then that's how you can think about it like a jelly bean. 2 jelly beans filled of like a jellies of the beans, and then when they collide, you can see they crack, and then the beans try to collide with each other. And but it's just kind of analogous. But here it's like the dimensions are so small. There's a lot of things involved. Means the probability of collision and how the number of actually collisions that can happen is kind of those numbers are tremendously unpredictable. I mean, at least unpredictable means they are actually calculable, but that is what gives the probability that how many protons at the end can collide. So if you look at on the table in the round 1 and round 2, round 1 actually lasted for 3 years in the beginning when LHC started. Then the round 2, you can see that the number of PP collisions that gets created initially was, in the round 1 was 3.5, observed 10 to 14, and in the round 2 was 10 to 16. But the number of Higgs events, which are actually the primarily this was the goal of the LHC experiments when it started, that to detect Higgs bosons. Okay, so those Higgs events are pretty much their cross sections are kind of low enough that you can, at the end of the year or per year, you can only get 10 to 4 events in the round 2, and in round 1 it was few tens of 10 to 2 events. So that means the analogy is that it's like fetch me my needle which is buried in those haystacks and do it as soon as possible. That means it's kind of impossible task, and if you think about just putting what is it called, 1 people, 2 people to find it, and within like minutes or seconds. So what it boils down to is one Higgs. Essentially, we're looking at a 1 Higgs event in 10 to kind of 12 events, that collisions that is created per year. So that is how much that is how low it is, the number of events that we're looking at to find and then and kind of verify that there's actually Higgs events, so that we can kind of understand if they're actually, we can verify that whatever the theoretical predictions were, that it actually did make sense. Okay, so that means this is where it boils down to, how can we do it? How can we find it and find it as soon as possible? So here is, and what actually are the obstacles in doing it? So in this slide, I will talk about kind of and event rates. Means when we collide proton and proton, it's pretty much hadrons, and from particle physics, theoretical particle physics, we know pretty much all the cross sections of all kinds of events which are which come out of these hadron collisions, right? So in this case, with the luminosity of 210 to 34, the input, I mean, we essentially produce almost 1 billion events, collisions, I would say, collisions, PP collisions, which amounts to 1 gigahertz input rate. And we need to keep good events, but the good events contain almost 50 background overlap, which means the events that we are looking for, those actually gets always contaminated with quite a bit of background. But in this case, one good event contains at least 50 background events. So in order to, how do we filter it? I'll go back to that one in the level 1 trigger. But so that is a good event. Then that good event, is a Higgs event we're talking about. We have standard model physics and standard model events which contain the W's and the top events. They come like W event comes at 1 kilohertz, top events 10 hertz. But so those are standard events. They actually occur no matter what, along with either particular the Higgs or hard event, I would say, the Higgs events. So we need to keep all the information so that we can analyze and get the output. And our ability to store, currently our ability to store the amount of events is limited to 1000 hertz, 1000 events per second that we can actually collect, and store from the detector. That means we have to throw away a lot of events that actually are not of interest, so that we can sustain our the storage and everything downstream. That we do that in terms of using the trigger system, which we have a level 1 trigger, which actually does reduce the 1 gigahertz PP interactions to 100 kilohertz, and then we use a second like another layer of trigger, which is called high level trigger, which reduces the 100 kilohertz to 1000 hertz. So that's the 1000 hertz we store. So on this particularly, you can see graph there. You can see all the cross sections on the left axis, the left versus particle mass, and the event rate on the right axis. So you can see what the numbers that I just talked about, you can see there's actually kind of clearly marked there, is that our ability we can only store up to 1000 event rate. So whatever within that, we need to detect all kinds of events, including the Higgs events too. So, but what are the challenges in doing that? First of all, detector, we need to make sure that our detector is designed in a way that we need to keep, we have to detect all the interest in the events of interest. So in that case, it should have fast response. It should be highly granular, and it must be radiation resistant. And those are actually, I don't want to go into the details because I want to focus on mostly the computing part. But then the second phase, the challenge is the event million interactions per second. We will only keep 1000 events per further analysis. That means we need to reject most of the interactions, but we need to preserve also sensitivity for rare processes that might escape that. Then the third and the other important that I am focused on, or I'm going to focus on, is the computing analysis. So we store 1000 hertz data, which essentially amounts to petabytes of data per year. And how do we analyze it in a time and get the result out of it in a time and publish it and essentially verify that the physics part is right. So in order to do that, we cannot use just we essentially need to use large scale distributed computing. That is something that we essentially found out from the very beginning, that just using merely a single data center is not going to be enough for this. So we focused pretty much on distributed computing, and that resulted in the grid computing kind of side of it. So here is a kind of a quick glimpse of the 4 experiments that are being conducted at the LHC right now, at least the primary ones. And you can see there actually the CMS is one of them, compact muon solenoid, which sitting on the top right corner of the ring. And the other three experiments are actually in the bottom of in the ring there, LHCb, Atlas, and ALICE. Atlas is also kind of has the same goal as the CMS experiment. So in order to, the reason is they decided to build two experiments so that they can complement each other in terms of verify that the results observed by one experiment is also observed by the second is kind of true, false. So just to make sure that there is no bias. So that is why Atlas and CMS, they do pretty much kind of complement each other with the proton-proton collision physics. The other two experiments do separate other studies there. Okay, so out of, as I said, I'm primarily going to focus on CMS. So here is a picture of the CMS detector. Just to give you overview of the detector itself. So in this case, the detector, it is a total, its overall diameter is 15 meters. Its total length is 21 meters. It has got a magnetic field 4 Tesla and total weight is 12,000 tons. But the important part is that this detector has been designed in keeping in mind that we need to detect Higgs and any other, particles that has not been detected yet at the energy scale that we are actually probing it. So that is why this is how the detector was designed. And the primary thing, of course, in this case, like any other high energy detectors, high energy physics detectors, as we know that we have charged particles, we have neutral particles, like charged particles are electrons, muons and hadrons, pi mesons like pi plus and kaons. And then we have leptons, which are electrons and muons. So we need, and then we have neutral particles like photons and pi zeros. And we have to detect all those particles which come out of the hadronic interaction from the proton-proton collisions. And that is why this detector has been it actually is made up of sub-detectors where the part of that is meant to track, measure the momentum of the charged particles and the charged particles, and this other part which is called the those are actually called tracking detectors that track the charged particles. Then the second other part of the detectors which are for catching the neutral particles like photons and pi zeros and other pretty much the ones that deposit energy, even electrons too, the electron energy deposit, those are called calorimeters. And this has got two kinds of calorimeter. One is a E-cal to capture the electrons and photons, and there is a H-cal which is called this is the H-cal which is for catching the hadronic hadrons there. And then we have the other ones called muons, and the muons are going to catch means they will essentially give a signature of the muons, because we know that muons cannot be caught. I mean, they essentially they just penetrate through meters of steel, so they cannot be stopped, they cannot be caught, they can only leave signatures. That is how, and that's why the muons are at the end of the muon detectors are pretty much at the completely outside of the entire detector area, because the muons will essentially penetrate through everything and then they'll leave signature, they'll escape there. So as I said, this is all designed based on a lot of studies to optimize, to catch everything that is possible, and so that we can find at least, the physics of interest like Higgs and others. Okay, now the data that comes off the detector, as I said, is the protons and proton, they're actually collision rate is 40 megahertz, and the event size, each event you can see comes out to be like 1 megabyte. And when 40 megahertz, if you look at this here, which comes out detector, that amounts to 40 terabytes of data per second. That's an unprecedented amount of data, 40 terabytes, and just like from one, the collision radius, that much data comes out every second from the 40 megahertz collision. And each event size is 1 megabyte. And at the level one, as I mentioned, level one essentially reduces it to 100 kilohertz, which means level one output is 100 gigabyte per second, this point. And then it goes through a high level trigger, which reduces to 1000 hertz, which means 1000 megabytes per second. So that's the amount of data we store at the end. So that's 1,000 events, 1,000 megabytes. So if you multiply it for 10 to the second, 10 to 7 seconds per in a year, then the data size, total data size for a year comes out to be of the order of, taking all the efficiencies and inefficiencies into account. That's like 20 petabytes per year. So this is what the main parameters here, 20 petabytes per year that we need to store and analyze. And it produces out of 1 billion events per year. And we have like almost several thousand batch and means users or physics analysts, like graduate students and postdocs and everybody, in order to, they are to analyze all the things. Okay. Now, coming back to the challenges, how do we do this? We have 10 to 20. What are the challenges that we can analyze so much data? So we have 15 to 20 petabytes per data per year. And this data processing and analysis requires hundreds of thousands of CPU code. And we have scientists in dozens of countries worldwide that need access to the data in real time. But the issue is that CERN can only provide up to 20 to 30% of the CPU and storage. Okay, so providing more is far beyond the funding capacity of CERN. So because of all these things, if you think about it, that centralized computing, which is supposed to be, we thought that it could be done at CERN using the CERN computing alone. It is not, it was not possible. So that means the centralized computing must be replaced with a distributed or a grid computing. So in the sense, grid computing, coming back to the grid computing now, this was actually, there's a lot of thought went into this grid computing. And if you, the concept wise, you can think about it, it's like it has an analogy to the power grid. Means, at home, we don't need to know where our electricity is coming from. So we just plug in our devices and we get it running. So that is exactly like that. In the computing domain, we don't need to know where our computing is done. Computing power is coming. We just need to plug in my laptop or my computer to the grid and all the computing is done. I just submit things. And then the second part is the data. I don't need to know where the data is. I can just plug into the grid and I can just fetch the data and put and install, store my data that I produce. So this whole concept of grid computing actually it came out or essentially kind of proposed by Ian Foster and Carl Kesselman in 1999. They had a paper which is called the Blueprint for a New Computing Infrastructure. So this is how the grid computing concept came, which is pretty much a distributed computing. And of course, as I said, the motivation was that, this grid computing is kind of composed of many network computers acting together to perform large tasks. That was the primary goal because it could not be done at a single facility. And of course, the second part is, if we have a lot of facilities, then we can keep multiple copies of data so that they can be accessed by scientists independent of their geographical location. And having a lot of facilities, distributed computing facilities, there is no single point failure, which means if one side goes down, then things, the middleware will take care of everything. They will all the tasks will be directed to the next another side. So there is no delay or no kind of loss in terms of analysis ability. And computer centers in multiple time zones, they will essentially ease round the clock monitoring and availability of export support. The other important reason was, the grid computing is that the resources can be distributed across the world. And for funding and sociological reasons, that actually has a large implication because, one country doesn't want to spend money in another country developing their infrastructure or putting money. So that's why any country that collaborating with this wouldn't want to put a lot of money into CERN, developing CERN's computing facility. So in that case, what was the right thing would be they can bring up a facility in their own country. And that means that facility can be used for multiple purposes. In this case, if depending on the requirement. So that actually was, so the money stays in the country, it creates jobs and all the kind of sociological reasons. Okay, so that was a primary goal too. And then the resource access control will be done through strong security, means there will be no unauthorized access and no malware, nothing. So those actually, so in this case, so keeping all these things in mind, it turned out that the effective solution to the data processing and analysis challenge of the LHC would be to have a grid computing. Okay, so the features are pretty much a grid facilitates collaboration between members of a supported distributed community, which means they can
Sir, is there any problem, sir, network issues? Because we are unable to hear, sir. Hello? Sir, am I audible to you?
Ajit sir, can you hear me? I think some network issue is there.
what is called South America, but then there are national, regional, and inter-regional grids there. So all these grids.
Sorry to interrupt, sir, but we are not able to see your presentation, sir.
Oh,
The screen is not.
sorry.
Ajit sir, screen is not visible.
Oh, okay, just a minute. Is it now?
Yes, sir.
Yes, yes.
Oh, I don't know why it stopped. Okay, please tell me where I left.
Just now the screen was.
Oh, just now. Okay. Okay, let me just go through it quickly. Okay, so here I was.
Yes, sir. Yes, sir.
Okay. Yeah, so I was just kind of saying that multiple viewers are actually possible. They can use the grid in parallel. Okay. Now, so there are many grid types, as I was talking about. There's the EGI, European grid, and then the OSG Open Science Grid in the US. And there are other national, regional, and inter-regional grids all over here, you can see. So what happened is all these grids that I'm talking on the top, these ones, they actually all existed some form or the other before the worldwide LHC computing grid came into existence. Means the worldwide LHC computing grid actually is a federation of all these grids. I mean, part of some of them, or and those grids, they were the basic starting point of the grid concept when they got formed, and they were in use for many, like at least 5 to 7 years that I know, or 10 years before they became a federation, which resulted in the worldwide LHC. So I will particularly talk about a little bit kind of the open science grid in the US, because I was part of that in studying 2005 when I joined UW Madison, because by that time the open science grid actually it came into existence and in 2005, and it is governed by the OSG consortium, and which means the consortium itself is made up of research labs, research collaborations, campuses, national labs, technology and software providers. Means pretty much these people, like many of those entities were part of this consortium, and they did successfully manage to kind of operate this open science grid. And its main goal actually was to facilitate access to distributed high throughput computing for research in the US. It is irrespective of the science. Means it was not restricted to any kind of particular science like high energy physics or anything. It was meant to provide the distributed computing to all kinds of research in the US. And the important thing was the OSG, again, OSG, that was formed in 2005, but it was built on and evolved using the existing infrastructure at that time, which is like there are campus grids, laboratories, the university experimental facilities. Those actually already were there, although they were not called a grid at that time. They were just kind of some kind of a distributed computing facility there. But those are already there, and based on the OSG kind of started, when OSG formed, they started using this and integrated all these things along, with the help of technology and software providers in the US. That is how the OSG came into. And one important thing, the last point here is it consists of computing and storage elements at over 100 individual sites spanning the entire US, which means this is pretty much the universities and the labs. And the nice thing about it is that a lot of sites, they have very few CPUs. Some of them are like literally a few hundred, and some of them are like thousands of cores. Means all of them is like pulling the resources together and using it for a common goal. So that is how the Open Science Grid was. And I essentially used the Open Science Grid from the initial 5-6 years to produce events like the simulated events for the CMS collaboration. So I was part of that OSG. And it actually, the OSG still exists, and that OSG became part of the WLCG. So the WLCG, the OSG still exists today. It is still kind of providing software and middleware support. Now that the WLCG was formed, it's pretty much, it has right now the WLCG, which combines 1.4 million CPU cores and almost 1.5 exabytes of storage over 770 sites in 42 countries. And more than 12,000 physicists around the world actually can access the data in real time, and they can process it. And it does. Sorry. And the important thing also that in order to allow only authorized people to access this computing grid, the WLCG has the infrastructure or the software or the middleware to establish the identity of the user, check their credentials, and searches for available sites for the request for the resources. Means there will be absolutely no unauthorized access to any of the resources or to the grid, which is a very important point to protect the integrity of the whole system. Now, as I already talked about this a little bit, but I just want to highlight one particular thing in the computing, LHC computing, in the WLCG, the model that is actually kind of followed, how to organize the computing resource and the storage resources at the sites that spans hundreds of, literally 100 countries, 100 sites, is something called a tier N model. Okay. And the tier N model is something that I'm going to focus on the next slide. So that actually was the core of this, the implementation, the core of the whole computing grid implementation, and how it really satisfied the purpose. Now, this slide does show that tier N computing model. So at the core of it, you can see the tier 0, which is at CERN. And then there are a bunch of tier 1s, which are actually distributed across many countries. Primarily for, depending on, for the CMS, we have 7 tier 1s distributed across, several European and US. And then there are tier 2 sites, which are distributed again across many countries. Then there are tier 3 and the tier 4. The goal is the tier 0 will essentially be at CERN, which produces the data, keeps everything there. That's the goal. Then the tier 1s, they will get most of the meaningful, like primary data sets with the details, and they will store everything at the tier 1 that has a copy at tier 0. The processed copy, I would say. The tier 0 keeps everything. Then the tier 2s are the important ones in a sense. They will keep the data sets which are meaningful for analyzing them. Means the users or the physicists, students, everybody, they will get access to that data which is stored at the tier 2 for a quick analysis. So then the tier 2 is actually the most important ones in that sense. Then the tier 3s, they actually belong to the, like they can be found at university level, like a small like individual users levels too, and then tier 4s. So in this case, what happens is, as I said, tier 0 will have all the data, then the tier 1s, then the reduced amount of data at tier 1, then the reduced amount of tier 2, then it goes down to tier 3. So here I'm focusing, here is a map of the WLC resources for CMS precisely. And it has got over like 70 sites worldwide, 350,000 computing cores as of now. And it has got at least 150 petabytes storage disk and more than 250 petabytes of used tape space so far. And you can see all this in India. We have at least, there are, I think in the TIFR is one of the tier 2 here. And okay, so here is another snapshot of that. As I said, tier 0 is at CERN, then 7 tier 1s, and 54 tier 2 sites. And the important thing is that in order to move all this data, petabytes of data across from tier 0 to tier 1s, so we have dedicated optical private network between tier 0s and tier 1 sites, which is governed by LHCOP, and this is called optical network, LHC optical network. And that actually kind of it runs under under the Atlantic. We have at least, I don't know how many fibers, I don't remember, but it's like a bunch of fibers running 100 gigabit network under the Atlantic Ocean. So that means the data again comes to the tier 1s from the tier 0 and gets distributed to the tier 2s. So here you can see is a kind of, as of yesterday, as I said, the total number of cores. This is a plot. These two are plots of the number of cores, CPU cores. You can see the tier 1s, all tier 1s is almost the 100,000 cores, and all tier 2s 250,000 cores. And you can see that most of the cores are pretty much all busy all the time, and very few idle cores, means just for the purpose. Now, coming back to, as I already quickly I mentioned that how the data flow happens from the CMS detector to the tiers. So the data comes out of CMS experiment, goes to tier 0, and then gets distributed to tier 1s and the tier 2s. What is important is the network, the network speed or network bandwidth. So essentially all the tier 1s are actually connected with the tier 0 at CERN with 100 gigabps network. And so here I'm just showing that the formula tier 1, which actually kind of handles all the, or is primarily responsible for the tier 2s in the US, they actually all connected through a between 10 to 100 gigabit networks too. And then from the tier 2 to tier 3, it can be between 2.5 to 10 gigabps. At that point, they can still manage, it doesn't have to be very high throughput in terms of network, because there the users mostly can submit, analyze or submit their workflows, and they can analyze. They don't need a lot of bandwidth for that. So this is the pretty much the data flow from CERN experiment, from the detector to the tier 2s. Now, what is the purpose of the tier 0? I mean, what actually they do? Tier 0 essential is the one that which stores all the data and creates a fast snapshot of the meaningful data that can be analyzed, that is analyzable. Okay, so that means it does calibration, alignment, recursion. So it's a lot of work it does, and then it passes on the meaningful data that for further processing to the tier 1 centers, which are for the CMS. There are 7, and the tier 1 centers are actually responsible for reprocessing the data, as needed. That's a very important thing. And then the tier 2s pretty much kind of are responsible for producing simulated data, and then keeping the analysis object data. This is what is called AODs, which are the most important data types that is used for user analysis, because the user analysis doesn't need to, at this point, the users don't need to go through all the fine details about the detector signals. They have already physics objects are already made. They are in the file, so they can just simply run their code through those data and those files and get analyze whether there's a Higgs event or not. So that is pretty much done at the tier 2 center. So the tier 2 centers are actually very important in that sense. Now I'm going to focus mostly on the US CMS computing here. because I'm handling, I'm managing the tier 2 center at UW-Madison. So I'll just kind of talk quickly about this. So this is where you see the formula is the tier 1 here, and there are 7 tier 2 centers. So Wisconsin is one of them. Now the goal of, just already quickly mentioned the tier 2 center, the role of the tier 2 centers are pretty much, they have to provide the computing services, but that is not enough. They also have to do a lot of other works in terms of supporting the local physics community, other sciences, and the open science grid and middleware infrastructure projects. But the primary functions you can see here is already listed there. So I won't go through that, but I already but those are actually very important. That is that is what keeps the experiment, I would say, the ongoing in terms of timely analysis, analyzing the data, and holding the data sets, storage, whatever is meaningful, and reanalyzing the data as needed, all the things. So the most important, of course, is managing the CPU and storage resources and keeping them operational 24/7. That is a very important thing. And of course, keep them correct data sets and provide and maintain the high bandwidth so that users sitting anywhere in the world, they don't need to worry about that their analysis is getting slowed down because they cannot fetch the data from a particular site which is not in their country. So the function includes a lot of important tasks, and that is, please, you can go through that one, Alan, but these are so because of this, the tier 2 center, the role of tier 2s are actually very important. They provide the users the analysis capacities. And then talking about the tier 2 at UW-Madison, it was in 2005 that the tier 2 came into existence, and it was funded and by NSF for 5 years, and it has been successfully being renewed the funding for every 5 years since then. And it's I think the UW, I'm actually the manager of the UW tier 2 Madison. Yeah, tier 2, Madison. And it is one of the top CMS tier 2s out of the 54. And we are actually, this tier 2 is supported by the Formula tier 1 centers, because that is how we are attached to them. Okay, so now just I will have several slides to show what exactly is there in a tier 2. And this essentially all the tier 2s have similar things. All the 54 tier 2s will have similar things. So I'm just giving quick information about what we have at Madison. So we have we have 18 racks worth of computers or servers that is in the, and then this is how it's distributed. You can see in the pods, and we have cooling. So that's the infrastructure. And the university actually provides the power for that and the cooling. Okay, so and then at the latest we have, as I said, we have, at least I have 14,000 cores there, CPU cores, which is a mix of Intel, AMD, all the latest series CPUs that comes into the market. And here you can see just the plot. Last year we provided 136 million CPU cores, and here you can see that the usage number of cores somehow going up. But although all these extra that you see around here, it is not from the tier 2, our tier 2 cluster, but in the campus, UW-Madison campus, there are other data centers where we internally can send our, can get the resources. So that is why you can see that it's going up. So we get them opportunistically. Okay, so that was the computing part. Now this is the storage resources. So just quickly go through. We have right now, I'm managing there to 11 petabytes of raw storage. And this storage, the software that we use, it's essentially kind of a commercial software. It's called Hadoop Distributed File System. And it can run on commodity hardware, means it doesn't need, it runs, it can run on any kind of hardware as long as it has some basic, basic features. And this particular storage is, of course, in order to serve so much data, you need a storage system that is fault tolerant and reliable. It should be highly available, means it cannot go down anytime. It should be up 24/7, and it should be able to scale, means you can increase it without any problem. You can just keep adding hardware to it. It will keep growing, and it should be able to provide high throughput access, means it should, we are talking about like, parallel kind of access. So that many users can access terabytes of data, tens of terabytes at any given time, slowing down the system. So this is what we have out here. And as for the other important component is the network at a tier 2. The tier 2 must be able to provide enough bandwidth to have access to the data and the compute by thousands of users worldwide. So essentially in this case, the network, our network essentially is connected to the Chicago the Formula Chicago with like a 2 by on multiple 100 gig network gigabit lines, the optical fibers, and at the same time it's also connected to other tier 2s similarly, because they're 100 gigabits. So that means there is pretty much no problem accessing as much data as many workflows, whatever, without without any compromise. So it's built pretty well. And here, so this is essentially, I'm just kind of giving you a quick glimpse. Those who are actually familiar with this IPv4, IPv protocols, since it's an engineering institute here, so we essentially support both IPv4 and IPv6 protocols. And if people know that IPv4 is a computer protocol and the network protocol, Ethernet, and this is going to run out of space, and that is why the IPv6 protocol was introduced, and eventually the IPv4 will cease to exist, and it will all move to IPv6. Anyway, so in that sense, these are some of the important points. Is that our wide area network is multiple 100 gigabit network, and we use both IPv6, 4, and we have all kinds of other things. This is, as I said, this is not for our own. This is not only our tier 2. It is all. It is available, or this is the standard configuration at all the other tier 2s. And besides that, we a lot of software and services that actually are needed to keep a tier 2 running in a sustainable manner and do the job. So here is one slide that what kind of software and services we use: file systems and job batch systems, and then storage, cluster management, and monitoring. So once you have all the hardware, software going, you need to make sure your hardwares are all being monitored, your software is monitored, performance is monitored, everything. Nothing should be able to, you cannot go down anytime. And if nobody, your systems are not compromised, so everything. So that's why the cluster management and monitoring is very important. And this is what a lot of softwares are also used to keep track of. I mean, all those things. And then anytime you also need to monitor the network latency and bandwidth, which is a very crucial thing, because you cannot have any network, slow down or go like gets into error state or whatever. So that's all been kind of monitored 24/7. And the important part is we get warned immediately if there is anything that goes, wrong or down or has problems. So it's a lot of software that is involved. And the other important thing is, of course, at the same time, we need, for the physics part, of course, the goal is to use the tier 2s to produce physics by, by the physicists and the students, postdocs. So we have to really do a fantastic job in providing the supporting the CMS user community. And this is what we do. And that actually involves all these tasks that I have already listed here. And of course, it includes supporting all the users, and they're providing enough documentation about the resource fair uses, policy, and then giving them accounts, all the things, and then help them with the softwares and the batch system, storage, and data transfers, and then troubleshoot their problems anytime they run into issues that they cannot figure out, and train them, all the things. And then the most important thing also is on-time response to all critical and non-critical infrastructure and operational issues that will affect. Okay, so those are the bulk of the tier 2. And I would say, so that means all the things that I highlighted is we have to do that. We have to maintain all these things 24/7. And means we want to make sure that nothing goes down. This site stays functional always. Now, into the future of computing. So I just talked about the grid part, and right now the grid part here is where the organizations, essential virtual organizations of users trusted by grid sites. As I said, this is essentially using a trust federation, means the users are all they are become the part of the VO. They get authenticated, they get approved, they get authorized to access. So that means this grid right now. The grid's access is through Trust Federation, and there is something called cloud, which into the future, of course, right now we have been already using the cloud model, which is, people are familiar with Amazon Cloud or the Microsoft Azure Cloud. So those actually are kind of similar Trust Federation to grids, but those are actually commercial clouds, which is not dedicated to any kind of experiments or particular business. There is kind of anybody can use them, and you pay for it as much as you use and all the things. So this is kind of economic this is based on the economic model cloud, and depending on the requirement in the future, the HEP experiments, the high energy experiments can use the clouds. We are already using the clouds right now to some extent, but it is not what is called. They actually economically they are not viable yet compared to the grid, where the sites, the experiments have their own dedicated tier 1, tier 2 sites. Then the next one is HPC. The HPC, which is called high performance computing, and that is part of the future. It is already there. We have so what this HPC is that many of, at least my experience in the US is, there are many of the national labs in the US which they have they get a ton of money from the department of from the research the funding agencies, and to install HPC systems, which are literally tens of thousands of cores, like supercomputers pretty much. And their high performance computing, part of that is that they are pretty fast supercomputers, and they can be, although they have been given to those labs for certain purposes, they can still be used by many of the researchers in the US based on the requirement. So the US, at least the US CMS community, has been able to get allocations in those HPC, in those systems. So that is based on the grant allocation scheme, where you have to write a proposal and you have to essentially kind of ask for certain allocations, and then if you are granted, then you can use it. But that means what is important part is the CMS, our workflows, whatever we develop for this, our grid-based operations should also work there. That means it has to be compatible. So that is where quite a bit of work goes into that. But it's right now we have been using the HPC, and but in the future, those will, as LHC needs more CPU, the processing power, we will probably go on directions where using clouds and HPC as needed. Okay, now, so this is a snapshot of the LHC that is right now, and how it will look after starting 2026 which is called high luminosity LHC. It will be in the future. So in this kind of plot, you can see we are right now we're the RON 3, which is going on 21, 22, 23, the year that is covering, and the trigger rate will be 1 kilohertz. Then we'll have a shutdown, which is called LS3, and then it will come back to something called high luminosity LHC, which is expected to run all the way through 2037, RON 4, RON 5, RON 6. But that means the CMS is on the path, or will be on a path, to exabytes of data acquired in the HLLH era. So that means a lot of things will change because the current computing capacity will not be enough. So we have to go for a higher computing, means more facilities or whatever needed to mitigate that one. So those are the things that is in the works right now. People are thinking about it, what to do. That will need a lot of things like adding more computing power, but money, of course, for that money will be needed. But then improving the software, which will do a lot, which kind of using machine learning and artificial intelligence, all the things to reduce the data size and to fine tune the algorithms and train the data so that the rarest of signals can be found in an intelligent and quick way. So those things are all in the works. I didn't put them in the slide, but those are actually part of the whole scheme. Okay. And then I would say my concluding thoughts would be, we are in the HEP, in experimental high energy physics. We are not innovators of modern computing technologies, but we actually are we are the ones who push for it the most. That is how a lot of things have come out from this. And using the grid technologies, the scientists and a team of engineers and physicists, they actually have been able to deal with the large LH data set and to do fundamental physics discoveries. And as we, as the advances in the telecommunications of the grid, cloud, HPC, computer technologies, go on, well, essentially the experiments will continue, continue to adapt to handle the increasing data volumes. And the best part, or the most important part, is that during this whole process, we train a lot of students and postdocs, and in various aspects of these things. Including software development, operations, and farmer development, and large-scale data analysis, which includes techniques like machine learning or artificial intelligence, all the things, so that they can, they can have a career they can